Welcome to my presentation, which is part of the webinar series of the EU project INCITE. The INCITE project wants to contribute to a sustainable European chemical industry by innovative chemoenzymatic integrated processes. My talk today is dedicated to the topic of flow chemistry in context of the project and picks up selected aspects of process and reactor development against the background of industrial implementation as followed in the project. My talk will give first insights in the corresponding project activities. Due to the confidentiality of the process, this is often done in a generic manner. My name is Patrick Loeb, and I'm the Deputy Head of the Division Chemistry at the Fraunhofer Institute for Microengineering and Microsystems, IMM, in Mainz, Germany. So, naturally, I will start with a short introduction just to introduce Fraunhofer IMM, the EU project INCITE, and what the role is Fraunhofer IMM is playing INCITE. But then I will go directly repeat some of the central aspects of flow chemistry as far as of relevance for the project. And then I pick up certain aspects which I want to show. And that is the process development, which is focused on transferring a batch to a continuous process, the scale-up concepts we are following, and then some insights into reactor development and the realization. And hereby we're using additive manufacturing technologies for the reactor development. And I will close with a conclusion. As mentioned, to introduce Fraunhofer IMM, and we are the Institute for Microengineering and Microsystems in Mainz, which is close to Frankfurt here in Germany, so in the southwest part of Germany. And we are part of the Fraunhofer Gesellschaft, also the Fraunhofer Society. The institute itself has about 140 staff members, overall budget in the range of 30 million euros. And so we were a bit of the Fraunhofer Gesellschaft. And you have to keep in mind that the Fraunhofer Gesellschaft has institutes spread all over Germany with about 76 institutes and research units, and in total about 30,000 employees working for Fraunhofer. And the research budget is of around 3 billion euro. It's important, so Fraunhofer Gesellschaft is a leading organization in applied research. With that said, I myself coming from the division of chemistry in Fraunhofer IMM, we have 3 divisions, energy, diagnostics, and chemistry, and I'm dedicated to chemistry. And what we do in the division of chemistry is just trying to improve chemical production processes and improvement in the context of product properties, efficiency, sustainability, and safety. And key enabling technology in this context are process intensification enabled by using the concepts and the devices of microprocess engineering. That means structured reactors and flow chemistry. So our solutions typically are in demand wherever small space, scalability, flexibility, and efficiency of a chemical process are required. To finalize the introduction, the general introduction, we are coming from the development and realization of microstructured reactors. So we have developed over the last 20-25 years, based on our microstructuring facilities, a broad range of structured reactors for different applications, covering heat exchangers, specialized gas-liquid contact devices, micromixers, or reactors for heterogeneously catalyzed reactions, and also for electrochemical synthesis. If I state, we improve chemical processes, mainly for fine and specialty chemistry, but also for pharmaceutical industry. We try to address it at the three level of components, the process and the plants. And these topics are interrelated. So it's important to have in each of these topics some knowledge to support the industrial customer to come to the industrial implementation. And you will see this scheme a little bit also in our project activities within the INCITE project. Let's talk shortly about the role of IMM in the context of the EU project INCITE. As you perhaps know, the INCITE projects will end up with 2 demonstration plants to demonstrate the new developed technologies around chemoenzymatic processes. And from the 2 process chains we have, one is dedicated more to oligochemical esters and the other one for fine chemicals, and here a chiral compound, and we will start from fossil-based and bio-based starting materials. And the core technologies are that around flow chemistry, photochemistry, enzymatic processes, and membrane separation. In our bit, the main focus of IMM role is main focused currently on the flow chemistry, and the process is also linked to membrane separation. The enzymatic process is a follow-up process, so I really can concentrate here on the flow chemistry part. And the products will be used for crop protection. As you also know, the project will be accompanied also by supporting actions like techno-economical analysis, socio-economic and regulations assessment, and sustainability assessment. I just mentioned this because the aspect of sustainability is important, and it's naturally clear that there is a supporting activity within the INCITE project following our process developments. So let's move on directly to flow chemistry. Just to start somewhere, I pick up a definition which is exemplary but not exclusive. In the book mentioned here, continuous flow chemistry is defined as, or flow reactors are defined that they consist of a network of miniaturized channels with diameters typically in the range of 10 to 500 micrometers and mainly constructed of glass, quartz, silicon, polymers, or stainless steel. If you look at the activities of Fraunhofer IMM in the past, our main material is stainless steel, and often the channel dimensions rather reaching larger dimensions. The smaller dimensions are typically used for mixing structures. For example, is here given the slit interdigital micromixer, where we really ended up with dimensions in the range of 40 micrometers and 60 micrometers. While if you go to micromixers for higher throughput ranges, you are already at 600 micrometers. And if you look at heat exchanger structures, they are also rather in the several hundreds micrometer range. And in the flow reactors we apply in the INCITE project, we go even a little bit higher to 1 or 2 millimeters. But it's helpful to have a starting point in this. The question is, the point is that these flow reactors, the structured reactors, are an enabling tool for process intensification. Yeah. I started here talking from microstructured reactors on, but it's clear that there are other reactor concepts benefiting from similar effects. To extend a little bit to flow reactors concepts. But the reason what makes them special, and if you pick up just one exemplary point aspect, the fast mass transfer is often mentioned. And if you look this specifically, for example, if you mix 2 streams and you have a millimeter thick fluid stream lamella, then it takes up to 500 seconds to mix it. Yeah. If you thin this lamella down to 10 micrometers, you have just a mixing time in the range of 50 milliseconds. So you see, you can improve, exemplary shown here, the mass transfer if you use structured reactors. Other effects you certainly had heard already are efficient heat management, short residence times, defined residence time, defined and regular flow patterns, that you have safe operation modes, and you have a small hold up. So if I have to summarize what are then the direct benefits from this, you have more or less an improved control over your process. And this improved control over your process in the intention you wanted leads also to improved process results that might be ending up better selectivities, yields, or safety improvements. So if you look at the benefits for flow chemistry for industrial uptake, this mentioned precisely control over the process is one central pillar of the benefits. But there are other ones, and one is certainly the basis, the precisely controlled process is also the basis to explore novel process windows. So it's quite clear if you have a better control over your process conditions, it's also easier to go to higher temperature, higher pressures, and still have a control over your reaction. That means you can explore really novel process windows. And then you have other operational advantages which are linked to the concept of flow reactors. For example, that the scale up is a little bit based on numbering up concept, and this simplifies scale up, for example. And based on these three benefits, you can derive three central pillars. You can derive the benefits for industry. It's the case that not all the benefits will be important for each reaction or industrial chemical process, and that depends a little bit on process and also on the interest of the involved industrial partner. But typically, if you have higher selectivities and higher yields, you end up also with higher energy and resource efficiency. If you have a better process reproducibility, you have less off specs. If you can tailor your product properties, you end up with a higher value product. If you have a small internal holdup, you have improvements on process safety. And this is an aspect which is of relevance in context of the INCITE project, for example. You have a straightforward scale-up approach based on numbering up. This enables also to come faster to the pilot and production phase, also faster time to market. You have a modular assembly possibilities which give you rise to a flexible and adaptable production concept. Generally, process amplification is linked to small equipment footprint. That means if you have need compact solution, for example, in the context of decentralized production, this is a benefit. And it's quite easy to, flow chemistry processes are quite amenable to process analytical technologies, and that a basis for process automatization. Now I want to pick up selected aspects concerning process and reactor development in context of flow chemistry. As mentioned, the process within INCITE is partly at least confidential. So I illustrate here one partly things by an exemplary reaction. Yeah. And I took here the synthesis on ionic liquid synthesis, which is an alkylation of methylimidazole with diethyl sulfate, because this reaction is quite generic, yeah, and also quite matching to what we are doing within the project. And you see it, when it's done in a batch process, you have to run the reaction until completion to circumvent tedious separation. It's a very fast reaction, typically with high exothermicity, so you can end up with hot spots. And this leads in batch processing that you need to slow dosing much below the kinetic limits, and that means too long reaction times and a reduced plant capacity. Then, due to the hotspots, you might end up with side product formation and a coloring of the product in this case, and this affects the customer's view on product quality. And then you have a safety aspect. In this case, it was the diethyl sulfate, which is a carcinogenic reagent, and then you want to minimize this amount, this reagent in the process. So there's similar challenges in the INCITE process, handling a reactive intermediate, for example, also reduction of processing time, and so it's an exothermic reaction. So it has some similarities to the INCITE process. And typically, the challenge you have seen, we have started with a batch process, with batch recipes, and then it was the task to show that it can be transferred in a continuous process to exploit naturally the benefits of a continuous process. And the typical setup we started with has been micromixer tube setup embedded in a thermostated bath. Then you need pumps to feed your reactants. You have the temperature monitoring, and then you analyze batch-wise at the end your product. On the left side, you see the typical installations, and also a similar micromixer tube setup was used also in the INCITE project at the very beginning. And then you see one of the first tasks have been the reduction of the reaction times down to minutes. Yeah, in the case of the ionic liquid synthesis, you see that the plot conversion as a function of residence time for different temperatures, and you see if you increase temperature, you end up naturally with an acceleration of the reaction speed, and so you end up with a full conversion in a few minutes range. This is important for implementation in a flow reactor because you try also to reduce the internal volume of the flow reactors, which reduces your fabrication expenditure. So it's quite essential. Yeah, if you end up with a process in flow with several hours of operation times, then you can go to other equipment and do not need an intensified flow reactor. Other optimization parameters could be to handle heat release and to select the right dimensions of the reactors. Good. So to set this a little bit in context of the INCITE project, so Fraunhofer developed in cooperation starting from the batch recipe, a continuous process at lab scale using methods and apparatuses of chemical microprocess engineering. So we reduced also in the INCITE case the process time from several hours to a few minutes. What is additionally, as not shown so far, we have a direct coupling of two steps. Yeah? And that means we are synthesizing in the first step a very reactive intermediate, where the target is to reduce the internal holdup because of safety reasons. And by this coupling, it was possible to reduce the intermediate of the reactive intermediate, also to reduce the inventory of the reactive intermediate by a factor of 100 to 200. Yeah? And this represents a fundamental process safety gain. So, but then is the next step the pilot scale. And this pilot scale means in this case about a scale-up factor in the range of 100. And by this reaching this scale, we want to keep the key characteristics of the lab installation. And this means especially keeping rough also the cross-section length of the channels used, yeah, in a simplified statement. To give you an idea, it's a very intensified process, so we end up with a reactor volume still in the range of several hundreds of cubic centimeters. This brings us to the topic of what has been the scale-up approach we are following, how to come from the scale-up rig to the pilot installation, as mentioned, with a scale-up factor in the range of 100. If you look in a simplified, it's a very simplified scheme. What we have used in the lab scale, we have a micromixer connected to a capillary tube, both embedded in a thermostated bath. You have the adducts entering and the product leaving the reactor. And if you go to the pilot installation, this has to be a little bit modified. So let's make a theoretical refined lab scale rig. For example, I do not want to put my pilot installation in a thermostated bath. Yeah? So I have naturally to think about how to preheat the adduct streams, and also I do not only to heat up, and I want to end up also in a reactor concept with parallelized channels. So we used a microstructured reactor in the theoretical refined lab scale rig with some parallelized channels. And then also I have to cool down my reactant stream. So I need an additional heat exchanger. So, and then what you see here, but in this simple sketch, the intention is still to have the micromixer untempered. So I'm realizing the temperature. I'm defining the temperature in the mixer by preheating of the adduct streams. So, and coming to the pilot installations, you will end up with a parallelization of the structured reactor parts, which is illustrated by this. Yeah, and as I mentioned, we have a scale-up factor of 100 roughly. So the questions, the central reactors follow the concept of operating several tens of microchannels in parallel, and this in a reactor module. And you have always, they resemble a little bit plate heat exchangers in this context. And so you have a sequence of heat exchanger plate reactor plate, heat exchanger plate, reaction plate, heat exchanger plate, reaction plate. But combined in one housing, and the difference may be a little bit that you have a central, the incoming fluids are distributed by a distributor and cover plate, and so the scheme shows the functional principle a little bit. So heat exchanger is integrated, as you can see here. And compared to former times, perhaps we worked in the former times quite a lot in realizing this reactor. Coming a little bit to the question of how to realize these reactors. In former times, we have, for example, worked with wet chemically etched microstructured plates, putting them together and laser weld them together. Or another fabrication procedure has been starting from the same wet chemically etched plates and putting them together and brace them together. But nowadays, we quite often use an additive manufacturing approach by selective laser melting. So you do not have the reactor module is done in one piece and not set up by several plates. And you see here rather lab scale modular reactor, which represents a little bit in real the reactor concept we have followed. What you have to say to the add to the realization of the reactor modules by additive manufacturing it, that we combine it with different processing steps. For example, bringing in the additional tubes is done connected by laser welding, for example, and you have also some fine precision working still to do to finalize the reactor concept. If I've mentioned, we are, as mentioned, Fraunhofer IMM is generally exploring using these additive manufacturing techniques for reactor realization, not only in context of the INCITE project, it's broadly used. And you see here other examples on the slides, also addressing different sizes of reactors and different reactor concepts. Yeah, and it's very important. Additive manufacturing allows you quite unique flow guidance concepts, and typically by a simplified manufacturing approach. And the lower row of pictures give you an impression of the structure precision you can realize by selective laser melting of metals in the meantime. You see here, for example, the typical dimensions and surface properties for an electrochemically or for liquid heat exchanger at 2 below 1. Just to show you this a little bit here. So we have talked a little bit about the realization of the reactor modules. Perhaps to say something to the design of these reactor modules. Naturally, the design of the reactor modules is supported by simulation efforts, for example, by COMSOL. You have seen our initial design. We have also always initial designs resembling a stack of microstructured plates. And then you do naturally some simulation. And the simulation is typically focused on issues like, do we reach a flow equal distribution? Because you have a stack of plates, parallelized channels. So you have to make sure that each plate or each channel receive roughly the same flow rate share. Yeah. So this is a very important simulation task, an optimization task. If you look at the diagram, for example, this shows where is the flow velocity given for different channel positions. And there you see here, if you have no good equal distribution in that case. So there's some room for improvement. Simulation, besides flow equal distribution, it's also very important to look at the heat exchanger performance, to look at the heat temperature profile in the reactor. And other topics to address are also typically mechanical stability and what is the pressure drop over the reactor. In the INCITE project, we are operating in the range of 5 to 10 bars. So this explains a little bit the topic of mechanical stability. If the simulation delivers at the first run not the right result, then you make a design alteration and repeat your simulation. If it's done and it's matching, then you have a design confirmation, and then it's going up to the realization of the reactor. And after the realization, you need also an experiment validation and use of this reactor. This brings us, here I want to show the INCITE reactor in a test rig for basic reactor testing. In this case, for heat exchanger characterization. The point is that the pilot reactor is designed for such high throughputs that we cannot completely characterize it here at IMM. So the reactive testing, the complete reactive testing will be done in the final pilot installation at the industrial partner side. But here at least we cross-check a little bit the key performance characteristics like pressure drop, or that the pressure drop is in the correct range, and also the heat exchange characteristics. And you see, naturally, if you test these devices at several tens of liters per hour throughput, you naturally need also equipment like an effective thermostat and also effective pumps and mass flow meters for the right range. So this is already equipment you need for implementing the flow chemistry processes and make a basic testing. And here I just want to show one exemplary result. We have, as mentioned, it's not possible to make the reaction INCITE here at IMM, but naturally we know roughly what the heat exchange characteristics should be. And what we have done, we just checked, heated up water to the desired temperature and checked if it's the performance is working for over the desired flow rate range. And you see that we, for example, the output, we entered with for room temperature water and would like to come out with 50 degrees of centigrade outlet temperature. And then you see that we varied throughput range on the reaction side from 5 to 400 kilograms per hour. And we ended up to a 90 kilogram per hour where the heat exchange performance is sufficient. And this is quite in a good range where we also will operate our reactor modules. So this is just one exemplary. Yeah? This brings me already to the end of my presentation. As mentioned, these presentations are just first insights and also on a generic basis. With the pilot operation, there will be certainly much more information coming up, and which will be also addressed in following up training activities. The presentation, as mentioned in the beginning, is part of INCITE's training activities, and in this case also part of the current INCITE webinar series. And I focused in my presentation on flow chemistry and on selected aspects of process and reactor development for industrial implementation. The address points, which I want to highlight, are the central aspects of flow chemistry, the process development from batch to continuous processing, the scale-up concept for continuous process and reactors, and also the reactor development and realization using additive manufacturing. What I want to point out is also that this presentation is at the same time an appetizer, or should be an appetizer, for the corresponding INCITE training modules, which are currently under construction and will certainly be, in my case, also completed in course of this year. And if you want to have already a first look in the existing training modules, I included here the corresponding link. At the end of my talk, I definitely do not want to forget to acknowledge also the contributions from my colleagues here at IMM, both former ones but not all current ones. And the same is true nationally also for the project partners involved in the INCITE project, but also in former projects. Not to miss to mention this, but because it's clear not all of this is IMM work. So I thank you for joining, and thank you for your interest. And I'm open for answering also questions in the following question and answer session. Thank you.